Good morning, grade pros. Welcome again to our Smart Caps lessons, where we will be looking again at the different aspects of your curriculum and your exam requirements. I'm Rollins, and I welcome you to our classes. If you have joined us only today, you should be aware that the lessons, which are Smart Caps, are proudly sponsored by VT Africa Holdings, and also the Basic Education Department and other sponsors. We welcome you to the group, to the session, so that you can actually interact with the material, the resources that we'll be sending. And to do that, you can easily log on to hellosmart.com, and there you will be able to do our assessments, which are online. You can simply sign up as a guest, and you'll be prompted to put an ID number, which is 598751. You simply add your name, and you are already in the game. So I know that you are smart, you are able to access this portal and interact with some of the work that we'll be doing. Now, yesterday, which was our previous session, we were finalizing or finishing with the topic of polynomials. And we went as far as looking at various problems, and some of the things that we're talking about had to do with all that. So I did give some exercises that I suggested that we can do. So those were homework questions, and if such a question, for example, you want to factorize this. So this one, the solution is right. You can simply use your trial and make an educated guess at the first factor that can go into Px, which can be, if you use x equals to 1, you will be actually successful, which means x minus 1 is a factor. When you have this, one of the factors in a cubic function, you generally have 3 factors. So you are going to need to divide the cubic function with this resultant factor to get the remaining factors. The remaining factors might at first appear as a quadratic expression, which you might need to further factorize to get the 2 distinct factors. So in the end, you have the three factors that make up your cubic polynomial, and you have actually completely factorized. So we had different questions around, and we talked about the factor theorem and how you can use to say that for any number that you factor in, if there is no any remainder if equals to 0, that means that particular x in that bracket would be the factor. So for example, if it was 1, then your factor is x minus 1, like that. If it was minus 2, your factor is x plus 2. So I guess you remember those kind of relationships. And in this case, we are being told that if that function to the half equals to 0, what is the factor? So the factor in this case would come out to be a, because when you make x the subject, after equating to 0, you get half. So those are the things that we started to be looking at, and it was a good kind of exercise to be dealing with all these different things. We also mentioned that in a situation where you have this, you can simply substitute your x equals to -1, x equals to 6, x equals to -half, x equals to 2, and you substitute it into this equation, and you might find out that by using one of these, you can get to your final answer. So it might be that you get your answer as D after you substitute this into the, so it will give you 0. So we talked about all that, and we also had that for a question that I posed to you, that which one is not a factor. So again, you just do your x equals to -3, x equals to 6, x equals to 3, x equals to -2. Then from there, you start to substitute all of these into the given expression until you get the one that is equals to 0. All those will be equals to 0. But if you get something that is not equal to 0, that is the answer that we are looking for, because we are looking for not. So it has to be that. So you find that maybe 3 of these are equal to that. The last one of them, which is B, as you can see here, B would not fulfill this result. So B will not fulfill this. Okay. And there was also the question of factorizing this completely. And in your doing so, you would realize that you simply need to make that educated guess once more and say which factor would go into this. So you could start with, for example, that, which means you're checking with x equals to 3. So if you do that, you end up with something like f of 3 equals to 3 cubed minus 19, 3 minus 30. So you want to see if this is going to give you 0. Okay. So you have something like 27. You might need your calculator, and maybe you have 57, and then minus 30. So by simple inspection, you will see that this particular expression is too negative. It's too negative. So it will not fulfill the question at hand, which is to find something that would give us 0. So it will not give us 0. You might be interested to find out maybe, so maybe you might leave this A for now. You try to go to B. You try to use that, because all these factors must fulfill the x, the f of x equals to. So if you were to try B, So that was A. B will be that x equals to 1. So when you do that, you get your f of 1 being 1 cubed minus 19, 1 minus 30. 1 minus 19 minus 30 is clearly not equals to 0. It's just 2 negative. So you might have to leave that one for now because it's not fully satisfying. Then you try, for example, C. You try x equals to negative 3 or any of the other factors. So f of minus 3 would be equals to, so this is just very similar to the other one that we did at A. These are quite similar. To save your work, you could simply see that the one is negative, the other one is, so A was positive and C is negative. So I can even pick it right there that my first term, instead of being 27, it will be minus 27, because this time I'm working with negative 3. And then the next term, which is supposed to be negative 57, because I'm working with a negative, it will be positive. Okay. Then the last term is not affected because it doesn't have any x. So if you check here, you see that this satisfies the function to be equal to 0. So this is a very promising lead, this one. So you might need to have to check now this one and then this one to be sure that everything is satisfying. And your answer, as you can see, is C. So if one of these factors don't fulfill your result, you have to abandon it and actually check D as a possible answer. So in the end, if you were looking at your homework, you would see that the satisfying answer here is C. Okay. So that was a bit of homework that I left you to have a look at using the remainder theorem and the factor theorem. So just to give you a quick rundown of what we set out to do in our brilliant journey that we took. We started with the topic, and in this polynomial talk, we defined what is a polynomial, which is to do with a term which has many actually terms that are related by having different orders or degrees on the value of x or whatever variable is there. And we said a linear function is not a polynomial because poly means many. So a linear function only has an order of 1 on the x, which is as complex, if you want, as a polynomial. So one of the polynomials we looked at was the cubic function or expression, and we began to look at ways to factorize it. And we say to factorize it, you can look for the common factor, you can group like terms, and then you factorize them in pairs. You can also try to get to a place where you can use the quadratic formula by simply using the coefficient, or you can use completing the square is one of the methods. You can also use your factorization knowing more about the factors that make up the different numbers involved. We also realize that you can use the long division, and that way can help you to factorize, as well as using the synthetic method. So with the synthetic method, you also are doing sort of the long division. Finally, we began to be very smart, and we started to use what we call the remainder theorem and the factor theorem, which theorems are hinged simply substituting a term that you think, for example, what I have on the screen. If I think that x equals to 3 is a root of this particular expression, then I put it through just like we showed here. If it gives me 0, then it means that x minus 3 is a factor of the expression. If it doesn't give me 0, the number that it gives me, that's the remainder. So that's how we set out to do and accomplished in dealing with the remainder theorem and the factor theorem. So as we proceed today, we are going to be looking at more of reinforcement of these different aspects that we've learned in a way of making sure that we use them in an exam setup and in combination with other situations. So that is your CAPS outcomes, and we might have a question like this where you want to look for the solution of this problem. So I'm just going to show you the question as well as the solution, because this is an example. So solve for x if you have a cubic function like that, which is actually an equation. So in my solution there, I wrote that you must start by finding a factor using the factor theorem. So you make your educated guess, and in this case, I try to use x minus 1. Let's see, x plus 1. So x plus 1. So which means I'm using that root to check if x plus 1 is a factor. So in doing that, you see that it fulfilled that the function gives me 0, which means that x plus 1 is a factor. But I'm expecting to solve this with 3 factors and actually get the solution. So what I could do from there is to also check that since I'm now remaining with I have the factor and the original expression, so I can now use long division, which we talked about previously, to now prove or to show that you can get your other factor or expression. So this will be our expression for the long division. Remember, on your long division, remember to subtract and also to get your 0 to be sure that you don't have a remainder. So if you get a 0 at that point, it still means that this x plus 1 is not a factor since it's leaving a remainder. So when you do your long division, you are ending up with that quotient on top, and you can now use your normal factorization. You can use even the quadratic expression formula to get your x. Any other tools you are versed with to get your factorization here. So when you factorize that, you get this, okay? Which means now we have 3 expected factors, and your x from those factors would be that. So that is the method to solve any polynomials that come, especially in this fashion where you must solve, which means they're equated to 0. You first look for a factor, and then you can divide that factor into the original expression using your long division. You can also use the synthetic method if you are happy with it, and you get your other solution by further factorization. All right, very interesting. There is another example that I put out for you, that if ax equals to x to the exponent 5 minus 2x cubed plus px minus 1. If it's divided by x minus 1, the remainder is negative half. Find the value of p. So in this case, take note that a is not an unknown. We know a is the function. So a is simply representing any function. You are used to f. Sometimes you see that it can come as g or h. So this is just a name of the function. The unknown here is p, which is within the expression. So with that p, we can use our factor theorem thus, and we substitute the given number there, or the factor, which is x minus 1. So we are told that this particular expression will not give us 0 as it is supposed to give if it's a factor. So it will give us negative half. And then from there, we make our p the subject, and we get p equals to half, thereby solving the problem of what p is. Okay. So today we are looking at different exam situations, as you can see, and we want to start to understand all these things together and in a more comprehensive way. So many learners kind of shy away from questions to do with trigonometry, especially the graph aspect. They think it's not a main part of trigonometry. They think since it's a graph, there's a lot that you be asked to do, and sometimes just for 3 marks or so. But actually, this is one of the areas where you can excel. It's very simple to do graph work, and usually graph work is a lot of, so you can simply know your general shapes of the mother graphs of your tan, cosine, and sine. Just 3 things. And then you are going to be actually looking at it in different transformations that comes. So, for example, the exam question can be like question 1.1. In the diagram, the graph of f of x equals to 2. So I'll just show you the important part here. So your f of x is 2 sine 2x. So it is drawn for the interval x, which is in that domain from minus 180 to 180. On the system of x's on which f is drawn, see alongside on the following screen. Draw the graph of, so you want to draw another graph here of gx equals to minus cos 2x for the same domain. Clearly show all intercepts with the axis, the coordinates of the turning points and end points of the graph. So you are being challenged to draw your own, since one of the graph is already drawn for you. And it should be a walk in the park for you, because you should generally know the shape of the cosine graph. But a few hints here and there is that if you check the graph of f of x that we started with, you will notice that it is having a 2, so it's f of x equals to 2 sine 2x. So these two affect what we call the amplitude. Okay, so the amplitude is how high and how low the graph will actually stretch in that direction, and your maximum and minimum points. So your amplitude would give you the maximum displacement from the central point. Either direction, it's always a positive number, the amplitude, but in our functions, it can be negative if now there is also other transformations at play. So in this case, 2 is our amplitude, and you can see from here to here, that's 2. So that is the amplitude that is highlighted here. If this was a 3, that graph would be reaching 3. If it was a 8, it would be reaching 8, and so forth. What about the other value? There is also another 2 on the argument of sine. So this 2 affects what we call the frequency. Okay. So your frequency is the part of the graph that tells you how fast or slow the graph is moving. But in essence, we are talking that the original graph of sine is actually supposed to be crossing like this, and then so that would have been sine x, but it's not happening like that, because besides the height, which is the amplitude we have talked about, there is also some kind of quick turn. You see, the graph is turning at 90, I mean at 45, it's already on maximum instead of being at 90. So that is determined by the 2 for the frequency. So this 2 divides our, if you want your wavelength, or your frequency in this case would be, so you have that instead of your 360, which is supposed to be your wavelength, you are going to have that one divided by 2 because of that. So you end up with 180 degrees as your complete wavelength. So the frequency will be doubled, but the wavelength will be halved. So in this case, your graph will be very quick in that way. So in just 180, it is complete wavelength, as you can see from point to point. So then the two halves to make a complete wavelength. So that is how these numbers affect. If there is any other thing, like maybe a negative here, if there was a negative, it would mean that we need to inflect our graph in the x because this is affecting the whole y function. So it's a reflection in the x, but we shall be looking at that on g of x. So to now draw this graph, you need to be aware that the other graph that you are dealing with is actually the graph of g of x, which is negative cos 2x. So cos by convention shouldn't be capital letter, even sign and tan. So you might see me writing some capital letter here, but if you want to be strict conventional, your cos must be small letters. Okay. So with that in mind, we want to look at the general shape of the cosine graph. So the cosine graph is expected to be like this. So it's supposed to be like so, like so. Okay. So it starts on apex or in its max, and then it flows that way and that way, depending on your domain. And our maximums would be at 0, at 180, and also at minus 180. So this would be your graph of cos x. But in this case, we have a minus cos x. So let's start by pointing out maybe the 2. Let's start with the 2. So this 2 will affect the frequency or the wavelength. And in this case, the graph will be a bit quicker than it's showing here. And so instead of having a 360 as its wavelength, it will now have half of that, which is 180 degrees. Then, so it means you are going to be moving a bit faster than this. And as you saw with the other graph, you can actually look at what is happening each quarter of the wavelength, or in other words, what is happening in each 45 minutes. So this graph would be pretty quick. It will be moving a bit fast. So it will almost faster than that. So, and another thing now is to say this would be your cos 2x, but we are dealing with negative cos 2x. So the negative is a reflection, as we mentioned in previous, that it's a reflection in the x-axis. Okay, so if you put a mirror on the x-axis, then you get your resultant graph. So just look at this paper graph, and now you want to reflect it so that it goes the other way around. So it will be more like that, and more like that. So I'm sketching this graph using the knowledge of the mother graph and what wavelength we have on a function. You might also use your calculator and simply on your calculator to plot the graph. And we can have a calculator session of it sometime, and so that I bring you the software to show you the different calculators you might be using. But you might be familiar with how you can easily get the different values of x for the function, and then you use that to plot a graph. So when it says start to end, your starting will be minus 180 on the to 180, because that's your domain. When you are asked to actually put the steps we are having here is 45 degrees, because that's the graduation we have here. From 0 to the next mark, it's 45 degrees or minus 45. So you are going to put 45, and you get different values, and you plot the graph. So either method, you see that you end up with a graph such as this. So you can see my cleaner graph that I plotted here. This is the graph of G, and then the other one was your original graph of F. So this is what you're supposed to plot using the very same explanation that we gave. So I hope you can see clearly what is happening in terms of graph work to do with trigonometry. So question 7 might be related again to this, and I mean the question 1.2. It says in the diagram the graph of 2 sin 2x, which was that original graph, is drawn for that interval. Write down the maximum value of f of x minus 3. That's beautiful, because we just talked about what is the maximum. How do we know the maximum? And in other words, you consider the amplitude. So what is your maximum here? Your maximum is for this graph is 2. So you're being told now to subtract 3 from that. So your answer will obviously be minus 1. So you see how we make it out, that the amplitude of this is 2, and then minus 3 will give you minus 1. Very interesting. Another question 1.3 would say, in the diagram, the graph of the same 2 sin 2x is drawn. Determine the general solution of f of x equals to g of x. So if you notice, we have that we have the very same graphs, and we want to find their general solution. So if we don't want to use the graph, we can use our calculator, which here is shown. So you have your 2 equals to 2x, and you bring your cos 2x on the other side, which means it will be in the denominator, so that you end up with tan 2x equals to negative half. The beauty part of it is that this the two functions have the same argument 2x, so you're able to marry them together into tan because it's sine and cos. So sine over cos is tan. Then to get to your general solution, you get the reference angle simply by putting half, not the negative. So you put half in your calculator, and then you get your arctan of half will be 26.57. Then you ask yourself that, but my tan is negative here. So if it's negative, it means I'm dealing with two quadrants that tan is negative. The one of them is the second quadrant. The other one is the fourth quadrant. So tan is negative in this quadrant. So hence we have this part. So remember, you still have your 2x. So say 2x, and remember in the second quadrant, your angles are 180 minus theta. So it's 180 minus the 26 to get 153.43. And then you say plus k 180, where k is an element of these integers. And so when you now divide by the two coefficients of x, your result will be this. So you end up with that. And then the other consideration in the fourth quadrant, you might use your different methods. You might want to use 360 minus theta. So that was used to get to this part, as you can see. Or you might just want to use minus theta, which was used in this case. So when you have all that, remember, you might want to know why it's 13 there. Remember, it's going to be 2x minus theta will be minus 20.57 plus k 180, where k is an element of integers. So you need to remove this 2. That's where you get to your negative 13.28 plus k 90, like that. Okay, so that's quite interesting. It means where the two graphs are meet, you want to find all those points in an expression of your general solution. The last remark I might pose to you is that if the same expression you are being asked to find where f of x is greater than or is less than g of x, what you simply do is you simply go on that original graph where the two graphs are meeting, if you want to use that, and then you are going to say what is this point. So you need to know this point and this point why these 2 points. You want a situation where your graph of f of x is less than the graph of g from 0 to minus 180. So it's only happening in this part. Take note that we are dealing with only from 0 to minus 180. So that particular part will give us this. So those 2 points that are in the, so I'm sure you notice this part. So then you end up with these 2 solutions for those 2 points, which you can also write in a range like this, or in the other way as a range. So look at these questions and reinforce your trigonometry in this case. So today's lesson was rich in variety, that we looked at different exams that has to do with some polynomials and also trigonometry, graph work, and how you can start to use your general solution, your points of interception, and all that. So it was quite very practical, and you can use your calculator for some of them. With that, I would want to thank you and wish you a wonderful day. We meet tomorrow for the topic of calculus. Thank you.